The modulus. Was it? No. How far is minus 64 away from the origin?
You get 64 because it's
64.
It's an absolute.
Yes. Okay, so it sits way down over here, but its distance, its modulus, is positive 64. Okay. So 64. What's the angle?
Should be pi.
Yes. Pi plus I sine pi. It sits over here. Remember, it's down here somewhere. 64 units that way, so that's the angle pi. Not too bad. On the left-hand side, we're going to write z or 6 cosine 6 theta plus I sine 6 theta. Because it's the sixth root we want to find. Okay? Let's keep move this bit. Okay. What's the modulus of our general solution going to be? The modulus. So r squared. So we need this.
6 root of 64, which is 2.
Yes. 6 root of 64, which is 2. So if or 6 is equal to 64, just taking the modulus, or is equal to the 6th root of 64, and that's 2 to the power of 6. So that's going to, or is 2. So if you want, you can talk about our general solution, which we'll start subbing into in a minute. It's going to start off with 2. Okay, well, yeah, let's do it step by step. What we did is we took this bit equal to this bit, and we can just skip to this. This equals this, the real part of the angle, the real part. So cos 6 theta equals cos pi. So we could say 6 theta is equal to pi plus what? So that's one solution. We want all the solutions plus 2k pi. So it'll hit it every time around. So that was the cos bit. That's why we picked cos and not pi, or sine, because sine gives too many. Right, but we need to divide by 6, don't we? To find theta. So we get pi plus 2k pi over 6.
Is this DeMoirves Theorem?
Well, this is where we have to choose carefully what we.
They should all be going back, right? Because this is the upper limit of our range.
Well, we'll see. We'll try 0 first. Oh, yeah. Yeah. We'll always try 0 first, and then we'll work off that. We'll see, can we usually go 0 and then 1, then minus 1, and then we'll have a look and see if it's gone too far in either direction. We go the other direction.
Okay. So is it always 2k pi?
Yeah, yeah. Yeah, so we're trying to do something that you can do every time now. So it's always going to be this because we're using cosine. Okay, so you can write, if you like, you can write this. I prefer the cos plus I sine. Cos pi plus 2k pi over 6 plus I sine pi 2k pi over 6. Okay. Yeah, there's a lot. So we're going to do a load of different solutions. We're going to let k equal to 0 for our first one. We're going to call that solution Z1. We'll put in 2. 6? Isn't there 6 solutions? Yes, there's 6 solutions. What do we sub in for all the k's?
We don't know the exact direction.
No, because that'll give us too many. Yeah. So some of them we'll definitely sub in some negatives. How many? Do we need to go 0, 1, 2, 3 or 0, 1, 2 and then minus 1, 2, 3? We'll figure it out. We'll just go positive until we've gone too far and then we'll do the negatives.
Could we not go positive, negative, positive?
You could, yeah. Yeah.
So how do you know that 0 is 2 immediately?
That's the root, right?
Oh no, I haven't finished it. That's 2. I'm subbing in 0 now for k. So that's 0. It's going to be pi over 6 cosine pi over 6 plus I sine pi over 6 because the 2k pi bit is gone. And that gives pi over 6. First quadrant. Root 3 over 2. 2 times root 3 over 2 plus I 1 over 2? Or I
over 2.
I over 2, which simplifies down. This can all go now because we don't need it anymore. Which is, yeah, root 3 plus I. Yeah. Okay, next one I'm going to pick is k is equal to 1, just to see. So that's going to give cosine, what's this, 1. 1 in here is going to give, what's that? 3 pi over 6, which is 3 pi over 6? Pi over 2, I think.
Pi over 2.
Yeah, indeed. Okay, that's going to give 2 times, what's pi over 2? Sine, cosine at 90 degrees, 0. Sine is 1i, so 2i. Next one, k over 2, or k2, is that going to be slurred? Well, 6 pi over 6 is going to be pi.
Which is our limit.
So it's still good, I think. K2 is still good.
So we can then reduce to like the next one.
Okay, so a 2 in there makes 5 pi over 6, you're correct, plus I sine 5 pi. But we can pretty much say that's as far as we're going to go that direction. What does this give then? 5 pi over 6, our knowledge, we have to use pi over 6 as our...
Negative root 3 over 2 for the cosine. And then positive half for the sine.
Negative root 3 over 2 for cosine plus... Yeah, it's yeah, not a conjugate, but minus here. Yeah, it's a reflection in the imaginary axis, I think. So we could probably sketch those 3. Quick sketch will show us where the first 3 are. First one, it's like here. Root 3 plus I, so yeah, around there. The second one is right here. And the third one is the reflection of this one, so over here. Okay? I have a second suspicion, if symmetry is a thing here,
We're going to reflect it on the real axis.
that this is going to be 1, this is going to be 1, and this is going to be 1.
Yeah, that makes sense.
To fit all 6 have to be equal. Yes, if it's equidistant, it has to be. We just, yes.
You could also just, that means that for the following ones, we would just tack a negative on the angle.
Is that like in like a test? There's a question like this. Could we just do that? Or should we like?
Yeah.
Okay.
Yeah, you could. You could find half of them if it's an even number power, and the other half would be the opposite. But will we pick? Do you want to pick one just to make sure? We'll do one more just to make sure we're on the right track. What will we do? So we've exhausted the positive numbers, so I'm just going to do k negative 1 because it feels like the easiest one to do. Positive inputs for k. Yeah, because we reached 5 pi over 6. I feel like another one is going to be too far. So we want them in this section, so they're going to negative angles. So minus 1 for k, so I'm working with this still, is going to be 2 cosine minus 1 here. That gives a minus pi over 6, I think? Yep. Minus pi over 6 plus I sine minus pi over 6, which gives what? Oh, it's cosine minus, so it's in this quadrant anyway.
It's the same as the other one, so we know it's a reflection of
Would
it.
it just be negative or half?
Half?
Well, that would be the negative 2 one.
No, you're looking at negative.
So it's root 3 over 2 again, isn't it?
Yes.
Root 3 over 2, 2 times minus root 3 over 2.
No, it would be positive root 3 over 2. Then
Oh, sorry, you got me right. Yeah. Plus minus minus a half I. Oh, jeez. I was doing the other one. Root 3 minus I, which is here. It's the conjugate of that one, isn't it? The other one's going to be this one, which is what? So this is root 4. This is the fifth root negative 2 pi or 2i. We don't even need to do it. And the sixth root is going to be the reflection of, which one's not reflected? This one, negative root 3 negative I. Yeah.
But what's the, what do we plug in for, K for the 6?
It would be negative.
Negative 2. Negative 2. And negative 3 is the one that works for this one. You can try it yourself. You haven't gone too far with negative 3. Because the original thing starts with a positive pi. So subtracting from it doesn't go as far. So it does work. Okay. How on earth does something like, okay, I haven't put in the last one. This is Z6. How does something like this 6 times give minus 64?
Well,
Well, the angle will be times by 6, wouldn't it?
divide by 6, which cancels out the 5.
Which turns into a,
But it's times by 2.
No?
no, the angle. If the power is 6, the power applies and multiplies by 6. So it'd end up with negative pi, which is right there. Yeah? Negative pi. What happens to modulus when we keep multiplying it? Well, it has that spiral effect that keeps, and it will end up 2 to the power of 6. If I multiply this would be 2 to the power of 6. That will apply in, and it will circle around until it hits way over here at negative 64. Well, 2 to the power of 6 is 64, and the negative comes from the angle. Okay.
You're doing